Okay, I hope I'm audible to all my students who are attending this online lecture for the introductory econometrics course. In this online lecture, I'm going to continue with the discussion of linear regression. And in this online lecture, we are going to start with the concept of multiple linear regression model. Okay, this is formally chapter 3 of the book I prefer to follow, which is Introductory Econometrics by Jeffrey Wooldridge. This is an introductory lecture. We are going to talk about how a multiple regression model is going to look like. How are we going to interpret the slope coefficients? Because now in a multiple regression model, the slope coefficients are going to be the partial slope coefficients, which are going to look at what's the impact of one of the explanatory variable xi on the dependent variable, keeping the impact of all the explanatory variables constant. So we are now going to analyze the partial effects in the multiple regression model. This is the first lecture of multiple regression. Okay, requesting all my students who are watching this lecture, please make notes. These notes are strictly from the recommended textbook, which is Wooldridge. So if your university is following Wooldridge for econometrics, you can safely rely on the notes I'm going to make you write. You don't need to pick up any other book or your PowerPoint slides. As long as your university follows Wooldridge, you can refer to the notes I'm going to make you write. So let's quickly start with the discussion of Introduction to Multiple Linear Regression Model in this online lecture. So I'm just writing the main heading for the sake of clarity. This is multiple regression model we are looking at. This is the first lecture within multiple regression model. Okay. And I'm also writing the name of the textbook for clarity. This is chapter 3 of the book Introductory Econometrics. Introductory Econometrics by Jeffrey Wooldridge. This is one of the standard textbooks we follow across the globe for the introductory econometrics course. Okay, so let's quickly, first of all, look at a typical multiple regression model. So consider a three variable, regression model. Which is gonna somewhat look like this. Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus u, where again y is my dependent variable, x1 and x2 are explanatory variables. Okay, y is the dependent variable, x1 and x2 are the two explanatory variables. And u is my population disturbance term. Population disturbance term, disturbance or error term. Or I can also call it as a noise component. Now, how we interpret beta 1 and beta 2? Now, beta 1 and beta 2 are the partial slope coefficients. Beta 1 and beta 2 are the partial slope coefficients. What will beta 1 now capture? So beta 1 is going to capture the effect of x1 on y, holding the impact of x2 constant. Holding the impact of x2 constant. Beta 2 is going to look at the effect of x2 on y, holding the impact of x1 constant. Okay. I can similarly generalize it by a k variable regression model. So let's look at a generalization. Let's look at a generalization. Consider a generalized k variable regression model, which is gonna look like this. I have y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus dot dot dot. I can extend it to beta k xk plus the population disturbance term u. You can see it has k regressors x1 to xk. You have k regressors which are x1, x2 dot 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 xk. Now, point to understand as a note is that by introducing more independent variables, by introducing more independent variables, independent variables are also sometimes called controls or co-founders. Okay, so I can write controls or confounders. Confounders. Okay, so the more independent variables I am going to introduce in the regression, the more I can isolate the effect of each of these explanatory variables on y. So I can write, we can isolate the effect we are interested in. We can isolate the effect we are interested in. The effect, that means the effect of a particular independent variable, the effect of a particular independent variable holding everything else constant. Holding everything else constant. Now, the point to understand here is, students, if I have less explanatory variables, I may have the error term, which may contain some factors which may be correlated with the explanatory variables. But if I have a lot of independent variables, then I can see the partial, or I can see the effect of one particular independent variable on the on the dependent variable y when I keep all others constant, all other independent variables constant. So now the OLS estimates I'm going to get, which are beta naught hat, beta 1 hat, beta 2 hat, beta k hat, these are called the partial effects. So I can say that the OLS estimates, the OLS estimates beta 1 hat, beta 2 hat, dot dot dot, beta k hat are called partial effects. Are called partial effects. That is the effects that control, the effects that control for all other factors. Okay, so I hope students are understanding. Now, in multiple regression model, what changes is our interpretations. When you interpret the slope coefficient now, what we learn is that it's a partial slope coefficient. And partial slope coefficients are going to capture the impact of that explanatory variable on the dependent variable when all the other confounders or explanatory variables or controls are kept constant. Okay, so I can make students write the second point within the note, that it is useful to understand. It is useful to understand the important result that shows that, it is useful to understand the important result that shows that instead of explicitly controlling, instead of explicitly controlling for everything by including additional regressors, by including additional regressors, we may alternatively partial out we may alternatively partial out the influence of the other explanatory variables beforehand. Of the other explanatory variables beforehand. So now what I'm going to discuss with all the students is the partialing out algorithm or the partialing out effect. Instead of just adding more explanatory variables in order to, control for the impact of, other variables, what we are going to do is uh, we are going to uh, partial out the influence of other explanatory variables beforehand. How are we going to do it? Let's look at the steps. So I can say that therefore one can show that the estimated coefficient one can show that the estimated coefficient of an explanatory variable, say xj, in a multiple regression model can be obtained in two steps. What will be the coefficient of xj? Beta j hat. So we are now going to understand how we can obtain beta j hat using the partialing out algorithm. Step 1. First, we regress the explanatory variable. We regress the explanatory variable xj on an intercept term and all other explanatory variables. All the other explanatory variables, and thus obtain the residuals. So students, in step 1, what we are essentially doing is, I want to estimate what? I want to get the estimated coefficient of xj. The estimated coefficient of xj is beta j hat. Now to obtain it, what I'm doing is, first of all, I'm going to regress xj on intercept term and all the other explanatory variables. And in that regression, I'm going to obtain the residuals. Okay, call it rj hat. So rj hat is the residuals I'm going to obtain when I regress, xj on the other explanatory variable. So I can say that rj hat is going to be xj minus xj hat. This is the actual value, and this is the fitted value of xj. Okay, so that means I'm going to show this through an example also in a few minutes, but right now I'm generalizing it. Step number 1, I regress xj on all the other explanatory variables as well as the intercept term, and I obtain the residuals. The residuals are rj hats, which is the difference between the actual value of xj and the fitted value from the sample. Okay, now step 2. Step 2, now I regress y. I regress y on the residuals obtained from step 1. On the residuals rj hat obtained from step 1. Obtained from step 1. Okay, And that is going to give me something called beta j hat, where beta j hat will be summation r j hat. Since as I goes on from 1 to n, I can write, let's say we have n observations. So rij hat times yi over summation rij hat square. Remember, this is the formula of beta hat which we get from the OLS. Now, in this particular case, we have regressed y on rj. Since we have regressed y on rj, our beta j hat will be summation rij hat yi over summation rij hat square. Okay. Now, when we do this procedure, what we're trying to do is uh, we are trying to obtain the residuals, because that is going to, control for all the other explanatory variables. So I can write that the residuals from the first regression, is that part of the explanatory variable that is uncorrelated with the other explanatory variables. So students, the rj hat I'm going to obtain will contain that part of xj which has nothing to do with the other explanatory variables. I'm repeating it. rj hat contains that part of xj which has nothing to do with or uncorrelated with the other explanatory variables. So when I regress y on rj hat, I'm automatically controlling for the influence of other explanatory variables. So I can write, therefore, the residuals explicitly control for the other explanatory variables. The residual explicitly controls for the other explanatory variables by removing any correlation they have with them. So automatically the slope coefficient of the regression of y on rj hat is going to denote what? I can write that, therefore, the slope coefficient of the regression of yi on rj hat, that is beta j hat, this is going to be the slope coefficient, represents the isolated effect of the explanatory variable on the dependent variable. So this whole process is telling us that when I regress xj, starting from the beginning, when I regress xj on all other explanatory variables and the intercept term, I obtain the residuals. And in the second step, when I regress y on the residuals, the coefficient I'm going to get will be beta j hat, which will automatically control for the impact of other explanatory variables, which is what I want in the beginning. Okay, now let me explain this through a very simple example also, so that it becomes absolutely clear to all students, because so far I was just dealing with a generic term, but now let's uh, take a specific example. Suppose the true regression model is Suppose the true regression model is as follows. Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus e. Now step one. Step one is I partial out the explanatory variable. I partial out the explanatory variable. Okay, that means suppose I want to look at the impact of, suppose I want to estimate beta 2 hat. Okay, so I partial out the explanatory variable. That means I regress x2 on the intercept term delta naught and on the other explanatory variable which is x1. And I obtain the residual, let's say R. So basically I run this regression. See, this was step one. If I go back to the previous page, look at this. Step one was what? Step one was regress the explanatory variable on the intercept term and other explanatory variables and therefore obtain the residual. What I have done, see, for this regression model, if I want to estimate beta 2 hat, what I do is I regress x2 on the intercept, the other explanatory variable, and I obtain the residual. So when I run OLS on this, I get x2 hat, x2, I get the following. I get this regression. Let me write this clearly. I get x2 hat equals delta naught hat plus delta 1 hat x1. And my residuals from the sample are going to be R2 hat. So I can say that therefore x2 after the OLS, x2 will be x2 hat plus R2 hat. This is the fitted value. These are my residuals. So from this, I can write that R2 hat will simply be x2 minus x2 hat. What is x2 hat? x2 hat, therefore x2 hat is the part of x2 that is explained by x1. That is explained by x1. Okay, x2 hat is that part of x2. x2 hat is that part of x2 which is explained by x1. Whereas R2 hat is the part of x2 that is not explained by x1. That is not explained by x1. So this was all step one, where I regressed x2 on intercept term and other explanatory variable, and then I simply obtained the residuals R2. Now step two. In step two, what I'm doing, I'm regressing y on the residual. Regress y on the residual R2 hat. Surprisingly, you will observe that if I regress y on R2 hat, let's say my intercept term is alpha naught, but the slope coefficient of R2 will exactly be beta 2 only, plus E. So what we learn is that the estimated slope on R2 is exactly the same as the OLS estimate of beta 2 from the original multiple regression. OLS estimate of beta 2 from the original multiple regression. So that means when I do OLS on this, I get y hat equals alpha naught hat plus beta 2 hat R2 plus E hat. This is the sample, this is the OLS version of it. And this beta 2 hat is the same as the beta 2 hat which I get from the original multiple regression when I do OLS on that. Okay, so now you can see that this beta 2 hat automatically controls for the impact of other explanatory variables. This beta 2 hat will only give me the impact of x2 on y, because it's automatically controlling for the impact of other explanatory variables. Why? Because beta 2 hat is the coefficient of R2, and R2 is that part of x2 that is not explained by x. That means when I'm running this regression, I am automatically controlling for the impact of x1 and only looking at the impact of x2 on y. So I can write that in this regression, so I can write when you regress y on R2, the estimated slope measures the effect of unique variation in x2, measures the effect of the unique variation in x2 on y ceteris paribus. That means keeping the impact of x1 constant. That is keeping the impact of x1 constant. This is the partialing out algorithm or the partialing out process, where we are partialing out the impact of other explanatory variables on the dependent variable. Okay, so I stop in this particular lecture. This was an introductory lecture to multiple regression, which is chapter 3 of Wooldridge, where we have talked about how to interpret the partial slope coefficients and what's the partialing out algorithm. Now, in the next online lecture for the Wooldridge Econometrics series, we are going to look at expected value of the OLS estimators under multiple regression. Expected values of the OLS estimator under multiple regression. This is something I plan to cover in the next lecture. So I stop in this lecture. I hope students have enjoyed this lecture. Any doubts, you can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschoolof economics@gmail.com. This is where I stop in this lecture.